Oh boy. Again, the auto underline, why it defaults to being kind of squiggly. I don't understand. There we go. Okay. So we said yesterday that if you dissolve an ionic compound, first of all, if you're going to dissolve an ionic compound, are you going to want a polar solvent or a non-polar solvent? If it's dissolving an ionic compound. Yeah. Polar. Why polar? Ionic compounds have charges, and polar compounds have charges, right? They have partial charges, but still they have charges, and it is the attraction between negative and positive that will cause those things to dissolve. On the other hand, if you want something that isn't charged to dissolve, definitely don't use a polar compound because it's going to be attracted to itself, not to the non-polar compound. So you would use another polar compound. You want to dissolve something polar, use something polar. If you want to dissolve something non-polar, use something non-polar. If you'd want to dissolve something ionic, you need to use something polar. Right? So if you want to dissolve salt, you're going to dissolve it in water, not in mineral oil. But we said that when an ionic compound dissolves, it doesn't just dissolve. What does it do? What happens to a big dumb rock like sodium chloride or calcium carbonate or whatever when you dissolve it? Yeah. Sorry? It breaks into its individual ions. Does anyone remember what term we used for that? It does start with a D. Dissociates. Good. Dissociates. So recall that aqueous ionic compounds dissociate. And to make sure we know what that means, let's look at an example. Let's say magnesium sulfate. I think that's what I put in my cheat sheet here. Yeah. So we could say that magnesium sulfate in its aqueous form is really, we write it this way for convenience, but really what has happened is that you have magnesium ions floating around. What charge do magnesium ions take? Yeah, very good. And those are dissolved in the water. And you have sulfate ions, which take a charge of -2, floating around. Now, we write it this way for convenience. I have no confidence that that is spelled correctly, but this is more accurate. So we usually just use the AQ nomenclature to keep things neat. But sometimes we want to write it as the separate ions because it can be helpful. So I'm going to say but, which of course you're not supposed to start a sentence with a conjunction, but that's okay. But sometimes it is helpful to write the ionic equations for reactions. Oh, fun fact, right has a T in it. And when we say writing an ionic equation, what we mean by that is that we would write A plus AQ plus B minus AQ instead of just writing that the thing is aqueous. This is what we're going to do most often, but sometimes we'll write it this way instead, and we call that an ionic equation. It's messier, right? You can see right away it's messier, right? But you'll see why it can be useful as well. So let's look at an example. And I think a case where it can be really helpful is looking at a single displacement reaction. So we'll look at that here. Example 2 will be an example of a single displacement reaction. Oh my goodness, I am so sorry. So we had magnesium sulfate up above. Let's react that with something above it on the solubility chart, and let's take sodium. So let's have sodium, and let's react it with, not the solubility table, the reactivity series rather. And let's react that with magnesium sulfate. And this is straight out of our, now why wouldn't it make that straight? There we go. This is straight out of our single displacement reaction lab, right? We took a solid metal and we put it in an aqueous ionic compound, right? What's going to happen in this reaction? What's going to happen? Yeah. Good. So on this side, what will we have? So magnesium by itself, it'll be a solid, right? And then we have to figure out what NaSO4 is. And we could do that pretty quickly. Sodium takes what charge? 1, which means that a single sodium would give away 1 electron, 2 sodiums would give away 2, 3 would give away 3, blah, blah, blah. And what's the sulfate ion? -2. So where does that line up? Na2SO4. Good. Does that feel comfortable? And we could check our solubility table. And if we do check our solubility table, we're going to find that anything with sodium is soluble. So this should be aqueous, right? Okay. There we go. How's that feel? Is it balanced? But it's pretty trivial to balance. What do we need to balance it? Yeah, just a 2 there. And now it's balanced, right? Okay. So now, from the balanced chemical equation, we can write an ionic equation. And the way we do that, by dissociating the aqueous ionic compounds. So let's identify what are the aqueous ionic compounds in this reaction. Sodium reacts with magnesium sulfate to give us magnesium and sodium sulfate. What are the aqueous ionic compounds? Sorry? Okay, MgSO4 is one of them. That's an aqueous ionic compound. And do we have another? Sorry? Na2SO4. These are the 2 aqueous compounds. Does that make sense? Okay, so when we write it, we're going to write what's called the total ionic equation. You'll see a little later why they call it total ionic equation and not just net or not just ionic equation. But let's rewrite it. So 2NaS, there's nothing to change there because these are not ions, right? Those are atoms, they're solid. Okay, but when we go to write MgSO4, what do we have here? MgSO4 is no longer going to be written as MgSO4 because when it dissociates, what do we actually get? Well, we actually get magnesium ions that are dissolved, and we get sulfate ions, which are dissolved. What charge do the magnesium ions take? Great. So these are Mg plus 2. And what charge do the sulfate ions take? -2. Good. This is the dissociated, or the dissolved. Excuse me. It is allergy season for Joe. Oh my God. In other words, when we drop the sodium into this solution, it's not bumping into magnesium sulfate. It's bumping into some magnesium ions, and it's bumping into some sulfate ions. They're separate. They're floating around separately. Does that make sense? They're not a single unit. They're all floating around. Now, let's look at the product side. What was our first product? Solid magnesium. Has that changed at all in this case? No, it's not ions. It's still just solid magnesium. But what has changed? Sodium sulfate. Now, when this dissociates, what do we get? Be careful. Yeah. Very good. And what do we know? Are those solid sodiums? They are aqueous. Very good. And what charge will they take? Altogether +2, but each sodium takes a charge of what? Very good. Very good. And then what else do we get? Yeah, SO4, and it takes a charge of -2, and it's aqueous. And that is the dissociated Na2SO4. Now, why bother with this? Isn't that just messier? And to start with, we can agree, is it messier? Yeah. But it's actually going to help us understand something or learn something really fundamental about this reaction. So the ionic equation is messier. But it helps us understand the nature of this reaction better. Like, let's talk our way through this reaction. And what we should notice is, really, what is happening to sodium? We have 2 sodium atoms, and what do they become? What happens to our 2 sodium atoms? They become 2 sodium ions. So what have our 2 sodium atoms actually done in this reaction? Yeah, specifically by doing what? Sorry? Losing electrons. Does that make sense? And this reaction makes that really clear. The sodiums go from being solid sodium to being aqueous sodium ions that have a +1 charge. In other words, our sodium atoms gave away an electron each. The reaction shows us that. So we can see that the sodium atoms give their valence electrons. And what did they give them to? Nope. Did sulfate get electrons? That's the thing, is when we normally form an ionic compound, that's how it happens, right? It gives it up. But actually it didn't give its electrons to sulfate here. Sulfate already had 2 extra electrons. It had originally gotten them from magnesium. They were stuck together. But sulfate goes from having a -2 charge to having a -2 charge. Did it get any electrons? Did it give any electrons away? Did sulfate do anything here? No, it's hanging around. What took the electrons from sodium? Magnesium, because it went from having a positive charge to being neutral. Does that make sense? We can't see that from the balanced chemical equation. But when you look at the ionic equation, it becomes crystal clear. Yeah. Yep, and that is because, again, if you were forming that compound by reacting magnesium with sulfate or sodium with sulfate, that is what would happen. But in aqueous solution, that's not what happens, right? Now, it's still the easiest way to figure out what's going to balance out, right? But the truth is that in this case, when the magnesium sulfate originally formed, the magnesium gave its electrons to sulfate. But when the sodium sulfate formed, because it's a displacement reaction, sodium didn't give its electron to sulfate. Sulfate already had those electrons. It had to kick out magnesium. And to kick out magnesium, it had to give it electrons. Does that make sense? So the ionic equation shows us what's actually happening in the reaction, which is interesting. So sodium atoms give, and electrons, interesting, give electrons, you know what? Shut up. To magnesium. And then what we notice too is SO4 2 minus doesn't do anything. We call this a spectator ion. This is also why when we did that lab, if the lab called for, iron nitrate, and I didn't have some iron nitrate, but I did have some iron chloride, I knew that I could just replace that and the lab would be totally fine. Does that make sense? Because the anion, that negative ion, isn't actually involved in a single displacement reaction. It doesn't do anything. There's plenty of reactions where the anion does something, but in this particular reaction, that negative ion is doing nothing. So, what can we do with that? Well, we can actually go a step further, and we can say, if it doesn't do anything, why am I writing it in this equation? For example, this reaction is aqueous, which means it takes place in water, which means if we wanted to, we could say we've got like 1,000 waters for every, don't write this, for every one of these things, and we start with them and we end them, but we don't write them. And why don't we bother writing water in this? Because it doesn't do anything. So we don't bother writing it. But if the sulfate doesn't do anything, then why are we bothering to write it? And so this leads us to the idea of what we call net ionic equations. Again, the slightly angled, it's just the wildest thing that OneNote thinks like, you know what this guy probably wants? An angle at like a line at 2-degree angle. He's going to love that. He's just going to love it. It's going to make him so happy. So, looking at this reaction, right? So we have 2 sodiums. I'm just going to rewrite this so we can kind of mess it up a bit. We can cancel anything that is exactly the same on both sides. Algebraically, remember, this is an equation. And given that it's an equation, if you do the same thing to both sides, you haven't changed anything, right? That's one of the principles of working with mathematical equations. So we can cancel anything that is unchanged on both sides. Now, they have to be exactly the same on both sides. Can we cancel solid sodium with sodium ions? No, they're different things. I will get that for you in just a moment. Oh, no, allow me. Oh, there you go. I'm going to force my glasses. That's okay. That's my commitment to you guys. This yields the net ionic equation. So with those sulfates canceled because they're not doing anything, what does this reaction end up being? Well, it tells us that if you take two solid sodium atoms and react them with magnesium ions in solution, what will happen? Bless you. You'll get solid magnesium, and the sodiums will become ions. That is what is actually happening in a single displacement reaction. Does that make sense? Whatever your anion is, it is irrelevant. It's not involved. Now again, there's 100 little sub-reactions you could do that do involve the anion, but the main reaction just does this. How's that feel? Not too bad? Okay. Does anyone have any questions about that before we move on? Yeah. And not the total ionic equation? Oh, again, the reason you would do this is to help you understand. So if all you're doing is laying out what reaction you're going to do, you just write the balanced chemical equation. But if you think about it, the balanced chemical equation for this, right, is 2 sodiums plus magnesium sulfate yields magnesium plus Na2SO4, right? When you just look at this, it implies that what happens is a swapping of partners, which is actually how we always teach it, right? That's how they teach it in grade 10. That's how I teach it in grade 11. But what's interesting is that when you actually look at what's really going on, we discover it's got nothing to do with partners whatsoever. Really what it's about is electrons. And really what's it about is who wants electrons more, magnesium or sodium? Magnesium. So if a magnesium ion bumps into a sodium atom, because magnesium wants electrons more than sodium, because magnesium is more electronegative, it will take sodium's electrons. Whereas the opposite isn't true. If sodium ions bump into magnesium, they won't take their electrons because they're not more electronegative. Does that make sense? So it actually totally reframes the reaction. This reaction is what happens. It describes it, but it doesn't tell us why it happens. But if you look at the net ionic equation, all of a sudden, it doesn't just tell you what happens, it tells you what happens and what is not happening, which is to say the sulfate isn't doing anything. Does that make sense? So it gives you a more granular understanding. And what's another type of reaction that involved aqueous things, where actually the solubility was a really important feature? Double displacement. And what do you suppose my next example is? That is correct. You guys are good. In time, you could be great. This should be example 3, I believe. Exempla gratia 3, a double displacement reaction. I actually double underlined this one in my practice note. I'm wondering if that's me being cute. I'm not exactly famous for being cute, but here we are. And I'm just going to single underline it here. I think it looks kind of obnoxious, actually. All right. Let's look at a simple double displacement reaction. Let's take sodium chloride. Would that be aqueous, solid? What would that be? If we do it in water, it will be aqueous, right? Just about every chloride is soluble. Every sodium compound is soluble. Definitely aqueous. And let's do exactly the one we did in our double displacement reaction. Let's react this with silver nitrate. And that is also aqueous. You remember the silver nitrate, very expensive. I was miserable about being like, make sure you don't waste this. That's what I sounded like. Oh, guys, don't be wasteful. And what did this react to form? What happens in a double displacement reaction? Good. And sodium takes a charge of +1, nitrate takes a charge of -1, so this would just be NaNO3. And what's the other? I'm great. Can't you tell? What's the other product going to be? Silver chloride. And silver takes a charge of +1, and chloride takes a charge of -1, so that will be AgCl. And sodium nitrate. All sodium compounds are soluble. All nitrates are soluble. So this is going to be soluble. It'll be aqueous. What about chlorides? Normally they're soluble, but what are the exceptions? Mercury, silver, there's a couple other I can't think of right now. But so this one will be a solid. And because it's a solid, that means that the reaction does happen. Good. So the fact that we have a solid means that this reaction takes place. I'm not. Oh, I owe you that. I will send that to you. I'm sorry.
Okay, it's okay. It's just
Yeah, no, we should send it along. You're going to look irresponsible, and that doesn't work for me.
Are you feeling okay?
Yeah, well, I'm good. My voice is doing a thing right now, but I'm good. I think any second now it's going to clear. Shut up. Yeah, any moment now. I'm not a dancing monkey, Sam Brady. All right, so now, yes. Again, no, but why do people talk to you? Why?
I'm the best person to talk to.
Oh, that's a good answer. I can't argue with that. All right. All right. All right. All right. All right. We're going to write it to... Shh, quiet. Quiet. Okay, so we're going to write a total ionic equation for this, and I'd like you to do so. Total ionic equation. Let's make sure we identify everything that's going to dissociate. Sodium chloride is going to dissociate, right? Silver nitrate is going to dissociate, right? And sodium nitrate is going to dissociate. But, oh, that's very orange. I feel like that's going to be the kind of highlighter that blocks. You know the highlighter you get that just totally covers your writing and you can't read it? You know, those cheap, when you buy some of those cheap ones are not the best. Anyway, sodium nitrate. All of these will dissociate, right? Because they're all aqueous. But of course, it's important to remember that sodium chloride will not dissociate. That, in fact, is why the reaction occurs, right? Because we have an insoluble product. So write your total ionic equation, but make sure when you do so that you don't dissociate the silver chloride because it doesn't dissociate. I'll take a sip of my coffee. Once I find it.
How do you lose your coffee?
This way? I don't know. I guess the answer is I didn't. It's my coffee. Yes. So yeah, but we're not. You're right, but we're not going to do that yet. So first, I want the total ionic equation. So don't cancel anything. Just write all the ions. So take a minute and do that. If you think you got it, come write it up here.
I'm so loud. Obviously, maybe, ice cold water and that time of night might have not been. Why are you asking me
Made you fun of Sarah.
Yeah, even though she can't post on social media, but you know. When you said it will do, they'll be like, I realize she can't post that.
As if she knows.
Still do it. Like, how did I get up? No, like, how did it like, hey.
I think so. That's what
So mindful of how much nicer Savannah's writing is than one. It's really lovely. Like that G, like that's a serious G. No, my G looks like it's given up on life. It's supposed to come back up and it's just like,
He has like different ways to write G's. Yeah, but both of your G's are different, like in the first one and the second one.
That's true. The second one looks more like a Y. They both suck.
I feel like personally attacked because that's what my G's look like.
No.
I think I like my first G better than I like my second G, actually. Yeah.
You like the one that's like flatlining?
It's got a bit of style, at least. They're not like Savannah's. Look how much Savannah's got style. Yeah.
That's how I write it.
What's the question? Okay.
Is this the first time you've ever decided against talking?
Yeah, what made you laugh?
How gross you Really? Yeah. I'll work no bite. I am that.
All right, let's take a look.
Oh, I ran out of room.
I know the one thing about these is they end up taking up a lot of room, right? But if we take a look, the concerns.
So concerned. Most of you know, we just turn my papers out of this grade. Go on.
There we go. So I'm gonna highlight those so we can see where they come from, right? Is that helpful at all? You can see that the sodium and the nitrate here come from the sodium nitrate. On this side, the sodium and the chlorine come from the sodium chloride, and the silver and the nitrate come from the silver nitrate. That's pretty obvious, but I think it doesn't hurt there. Now, we would never actually bother to write this as a separate step, but just here for neatness sake, we're going to cancel out the spectator ions, and I'm going to rewrite this equation above, which again I would never actually do, but
Why are we doing that?
because I want it to be clear when you check your note. I especially hate my Q's, which should look like that. I kind of do a semi-cursive Q, and it's not nice. Anyway. That's better. Okay, so let's be on the lookout for things that don't change. What doesn't change? Yeah, if you look here, we start out with some sodium ions floating around, and we end up with some sodium ions floating around. What else doesn't change? Nitrate. We have some nitrate ions floating about, and we have some nitrate ions. In fact, let me use a different color so we can really kind of see clearly. We have some nitrate ions floating around and some nitrate ions floating around, and they are unchanging, so we can kind of get rid of them. Which means that when we go to look at the net ionic equation of this, what's actually happening here? What's actually happening? Well, what's really happening is that a silver ion, I'm going to change the order of these, and I think you'll see why. A silver ion is floating around, and what's it bump into? A chlorine ion. And when these two things bump into each other, what happens?
It's not a phone call, but I trust you.
Okay. What happens to them? They come together and they form what? Yeah, it turns out that a more energetically favorable thing, a more stable thing than them being ions in water, which is quite stable, even more stable than that, is the solid compound silver chloride. So a double displacement reaction, what we observe to be a double displacement reaction, is actually just two ions bumping into each other that form a stable compound that won't dissolve. Does that make sense? That's what's actually happening. So we can make this happen by mixing sodium chloride with silver nitrate, but the chloride has nothing to do with, the sodium has absolutely nothing to do with it, and the nitrate has absolutely nothing to do with it. You could pick any chloride you want, and it won't change this reaction because the sodium isn't doing anything. So potassium chloride, you get the exact same reaction. Rubidium chloride, barium chloride, strontium chloride, calcium chloride, magnesium chloride, beryllium chloride, wouldn't matter. You'd get the exact same reaction. Likewise, the nitrate doesn't matter. So anything that would have been soluble with silver will work. You could have had silver chloride. You'll get the same reaction. Not many things with silver are soluble. So your options are kind of limited in that regard. But the ions that are spectators aren't involved in the reaction. Yes, sir?
I don't get what we're doing. Like, are you under cancel spectator ions?
Sure. So we're looking for things that haven't changed. Because if they haven't changed, why are we saying they've reacted? So we have here Na plus ions, and we have here Na plus ions. Is there anything different about this Na plus ion than that Na plus ion?
It's with a different thing.
But it's not with a different thing. That's the point, is that they're floating around freely. That's the whole point of dissociation, is that even though we write this in shorthand as NaNO3 dissolved in water, when NaNO3 is dissolved in water, it's not NaNO3, it's Na over here doing its own thing, NO3 over here doing its own thing.
Show that reading for me.
Was that really helpful? Do you feel like you really understand it now?
For all of if the reaction occurs, does that mean that like it doesn't change? Because doesn't mean it does not dissociate if the reaction happens well?
Good question. For any double displacement reaction that happens, you'll have to have something here that doesn't dissociate. Which, boy, wasn't that a great example? It was a perfect question leading into the fourth example. That's because you guys are asking good questions. You guys are asking good questions. So here we go. Example 4 will be a double displacement reaction that doesn't happen. It's a really long title, but that's okay. Because we've said that a reaction doesn't happen. Yes, ma'am. Don't steal my thunder. Yes. I said don't steal my thunder. You're stealing my thunder. I have so few things that bring me joy in life, and you just stole one of them. Everyone was going to be amazed. They were going to go, oh my God. No, it's good. You're exactly right. I feel abashed. Anyway. All right, so let's react. Sodium chloride, its aqueous form, with magnesium nitrate, which of course would be MgNO3 because magnesium wants to give away 2 electrons. Nitrate can only take 1, so need MgNO3 What would the products be here? Products. Yep, NaNO3. Very good. Excellent. Very good. Yep, exactly right. And to balance this, we're going to need 2 of these, and we're going to need 2 of those, right? Did I get that right? And if you look up, you'll see that nitrates always dissolve in water, so that's got to be soluble. You'll see that nitrates dissolve in water, so that's soluble. You'll see that chlorides are soluble unless it's a bunch of things, and magnesium in one of them. So all of these are aqueous, right? Okay, so if we went to make this a total ionic equation, oh my God, the angle. Why the angle? So in this case, we would get 2 sodium ions, right? And we would get 2 chlorine ions. And we would get a magnesium ion. And we would get 2 nitrate ions, right? They are separate now. The 2 goes in front because they're not stuck to each other. They all float freely, right? And on the other side, what would we get? Well, here we would get 2 sodium ions, and we would get a nitrate ion. 2 of them, right? Because the 2's in front there. Yep, good call.
Would you not be adding magnesium and nitrate together in the first?
Sorry? Oh, yeah. Sorry, there should be a plus sign between them. Very good. And then we'd get a magnesium ion, right? And we would get 2 chlorine ions, right? And Autumn, what do we notice? They're all dissociated, and none of them changes, which means that they are all, yeah, they're all spectator ions, right? If you look here, the 2 sodiums and the 2 sodiums don't change. The 2 chlorines and the 2 chlorines don't change. The magnesium and the magnesium doesn't change. And the 2 nitrates and the 2 nitrates don't change. So, when we remove the spectators, there's nothing left. We get the null set. And that's why we said, if everything is just soluble in a double displacement reaction, then there's no reaction. Because there's literally no reaction. Nothing happens. Nothing changes. And a reaction is when things change. No change here. All right. I'm going to give you a little homework. My and symbols are really bad. Is anyone able to do a really nice, fancy and symbol? Like the ampersand, like this guy. Yeah, that's what it's called. Do you know what the root of ampersand is?
Oh, like how it became.
Like, do you know why that symbol is it?
You explained it in like function.
Oh, did I once?
Yeah.
Do you remember?
Yes. It was like, it was originally like per sand, like the 27th letter.
That's right. And because it was the last thing, that's where the name comes from. What about the symbol?
Okay, yeah, I don't think you explained that part.
Does anyone know? It's actually really obvious if you, like everything else in math and science, if you speak Latin. The and symbol,
Like we speak Latin.
the and symbol is just that, which is et, which in Latin is and. Yeah. So, like you probably learned at some point in your life, like the Wilfred Owen poem, Dulce et decorum et pro patria mori. No? Really? Did you actually not? Like for Remembrance Day or anything? How sweet and fitting it is. And one day you'll learn that oft-repeated lie, dulce et decorum et pro patria mori, sweet and fitting to die for the fatherland. What do they teach you in school? Good Lord. Anyway, read a poem for God's sakes. Go read some poetry tonight. That's going to be the next thing on your homework. Yes. But hell, you can read it. Guys, you can use your phones to read the poem. Oh my God, it'll feed your addiction. It'll be great. You can stop twitching for a minute. You'll be like, oh God, oh, there it is. Oh, thank God. And then you could Google poem and read it and be like, oh, wow, I've just enriched my life. Honest to God. Anyway, aluminum reacts with copper 2 oxide. Two.
Oh, you know what really likes about the boss is the one where he's like talking about like ice and fire or something like that.
So good. So good. There you go. That's your homework. Do it.
Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction ice is also great and would suffice. Thank you. Thank you.
You write that?
That's Robert Frost. That's my favorite poem from him. Sorry. I mean, I did write oh, you know what I mean? She's smart. No, she's so good at chemistry and math. Yeah. She's also a bigger nerd in her own areas.
You get a lot. No.
Yeah. What's up?
Where do I put all the marks for the assignments? Is it still on the spreadsheet or?
We'll have to make a page for it.
Okay.
I can do that.
Alright. Sorry that I'm late today. I got my blood drawn and I
That's
passed
okay.
out. So.
Oh my God, are you okay?
I'm fine now, but like I was supposed to be back like 8:30.
No, that's okay. We don't want to pass out.
Yeah.
Did you give blood or was this like